So just as a preamble for our next example, I'm going to talk a little bit about logarithms and harmonic numbers. So I'll dedicate some more time to logarithms in the future. So let's first start talking about logarithms. So I have a very basic question. So you can imagine this like as follows. So very often when I have a function, I give you the input, it produces output, like our machine at the beginning of our session. What if I asked you about the opposite? And in particular involving exponents. So this is really what we want to know about, is given x and b here, what power of y, so what should I make y to be such that b to the y is equal to x? So this is in contrast to the inverted question of this, which would be, I give you b and y and I want to compute what x is. I want to know what y you use to give me back x. So suppose, just for an example, suppose that b suppose we have powers of 2, just for sake of simplicity here. So let's sort out some powers of 2, okay? So I got 1, 2, 4, 8, 16, and we could write this up to some power, 2 to the power of n, for some n. So I could rewrite this to be 2 to the power of 0. I could rewrite 2 to be 2 to the power of 1. 4 is 2 squared. 8 is 2 cubed. And of course, 16 is 2 to the power of 4. And naturally, 2 to the power of n is just 2 to the power of n, right? If I ask this question to you, what should be down here at the bottom if I were to look at this from left to right? What should be y in each one of these cases? So I have 2 to the what is equal to 1. I got 2 to the what is equal to 2. 2 to the what is equal to 4, and so on, right? Well, this would be 0, then 1, then 2, then 3, then 4, all the way up to n. So a function that describes y is called a logarithm. A function that describes y is called a logarithm. So the base of the logarithm, or what we have for our powers, so in our case we have powers of 2, this number here, this b, is referring to the base. So often when we talk about logarithms, it'll have some base. So very often we'll have it as base 2 in computer science circles. So it's a logarithm. That's an a in there. Let me just rewrite that. So just as an example, if I give you log base 2 of 8, notice that, remember, like I said, 8 can be rewritten. So I have log base 2 of, that's just 2 cubed, right? So notice that the exponent here would be a 3. So 2 to the power of 3 is equal to 8, right? So notice that this is just simply asking, given the base, so base 2, this is the base down here, and given x, I want to know what y is. So this is what x is, and I want to know what y is. So notice y has to be 3 in this example. And another example, if, say, for example, I give you log base 2 of 1, what would be the result here? So it's 2 to the something is equal to 1. So what would that be? It's 0. So because 2 to the power of 0 is equal to 1. So if you have log base b of 1 for any one valid base, then the answer would be, sorry, that's not 0. No, yeah, it's 0. Yes. Sorry, I'm getting very excited here. Yeah, it is 0. Remember, 2 to the power of 0 is equal to 1. Yes. So now I'm going to define another thing for us. So we have logarithms here. And by the way, if you have any questions about logarithms, don't hesitate to bug me. I'm very happy to answer any of your questions. The other notion I need to define for you is what we call a harmonic number. That's the other piece or ingredient to this discussion. So harmonic numbers they're well known in series. Like if you talk about, say, a harmonic series, this is a well-known number sequence. But we're going to talk about the harmonic numbers. So given some n greater or equal to 1, the nth harmonic number which will be called h of n, is equal to the sum from I is equal to 1 to n of 1 over I, which this is just 1 plus 1/2 plus 1/3 plus 1/4, all the way up to 1 over n. That's what the nth harmonic number is. It's the finite version of the harmonic series. There's an infinite version of it as well, but it's just the nth or finite harmonic series. So, anyways, I must stress that in some circles, you'll see the nth harmonic number written like this, but for the sake of simplicity, I'm just writing it literally as a function like this, just for the sake of not needing to follow a convention, but for simplicity, I'm just writing it as a function directly, without having this cater to one community of how they would write the nth harmonic number. Okay, so here's the claim. This is the claim. We're going to prove that H is big O of log base 2 of n. This is what we're going to prove. You're going to see very quickly that this is going to be a little bit different than some of the other examples I've shown you. But at its heart is the same set of reasoning. So let's do the proof. So we find constants. Remember, we find the constants. That's what we're trying to say, what we're going to do. We find constants. We have a positive real constant, C, and a positive integer constant, n0. So that for all n greater or equal to n0, h of n, the nth harmonic number, is less than or equal to c times log base 2 of n. Now, we're going to have to deal with some cleanup here. Okay, so we have to be a bit careful about this. So the one thing we're going to watch out for is that we want to make it so that this nth harmonic number, I could try to make it and tie it to the next closest power of 2. So I'm going to try to round it up to something that looks like a power of 2 in relation to it. So I would like to make n, so now you might say I'm like doing with the harmonic number, but what I actually want to do is not actually that. I want to make n be rounded up to the next highest power of 2. So that when I talk about, you know how we had our example over here with the logarithms, where you'll notice that if I can get it so that the power of 2 is expressed literally like 2 to the power of n, notice that the result of the logarithm would be an n, for example. I'm going to try to do something like this to simplify our calculations. But it's a bit of bookkeeping. So to keep in mind that this is some bookkeeping. If we have some more analytical techniques, we can drop this entirely. But that'll be something I'll talk about in the future. That can actually simplify this analysis even further. So before this, before we do this, before we try to find c and n0, so before we do this, let n be rounded up Now, if you're not sure what I mean by this, I'm saying that if I give you a number, if it isn't a power of 2, then if it's something that is, say for example, like 2, like 2 is in fact a power of 2, right? It's 2 to the power of 1. If I give you 3, notice that 3 isn't a power of 2, but 4 is. So what I want you to do is not round it down to 2, I want you to round it to 4. So I'm always going to round up. So I'm going to take whatever that number is, I'm going to make it so that it is in the form of the next highest power of 2. So for example, if I give you 5, I would like you to make it into something that looks like an 8. So I'm going to give another variable to give that as a name, okay? So I'm going to give a name to that. So let m be rounded up to the next power of 2. Next power of 2. So that m is going to be the name of that. M is going to be 2 to the power of log base 2 of n with the ceiling function. Now the ceiling function, for those that are not acquainted with this, it simply says, hey look, if I have, so I'm keeping this very simple. If I have a number like 2.3, I would like you to write it as 3 if you apply the ceiling function to it. If it's 2.001, you apply the ceiling function, it has to be a 3. If this was, say, 4.3, you'd make it into a 5. These are all examples. It just says, whatever you have, make it the next largest integer. If it is not an integer, make it the next largest one. So that's what this is doing, is it's just saying, okay, say for example, like I said, if I give you 3, well, log base 2 of 3 would be something between 1 and 2, right? So that means that this will be something that will be like 1 point something something. So I'm rounding this up to 2, so that makes m equal to 2 squared, which is just 4. Okay? So that's what this is just doing here. And one thing I really want you to note is, because I'm rounding up to potentially a larger number, if it isn't the power of 2, we can say right away that, note that n is less than or equal to m. And then another thing I'm going to do is another bookkeeping thing I'm going to do is I'm going to let k be equal to the ceiling of log base 2 of n. This is just to save some space. So just keep in mind that k is always going to be the ceiling of log base 2 of n. So just as an example, if I wrote that in the previous sentence, it would be that m is equal to 2 to the power of k. So these are just some 2 bookkeeping things that we're going to need for our analysis to keep this nice and slick. So now we get to the good stuff. And the following. And as follows. So let's watch what we got here. So now remember, I'm just going to write out what the definition of h of n is. So let's write out what that is. So h of n is equal to the sum from I is equal to 1 to n of 1 over I, which this, because of the way we defined it, right? It has to be that it's less than or equal to the sum from I is equal to 1 to m of 1 over I, which this, if you think about it very carefully, is 1 plus 1 over 2 plus 1/3 plus 1/4, all the way up to 1 over 2 to the power of a something. What is the something? Well, it's m, right? So this would be 1 over m. But what's m? It's 2 to the power of the ceiling of log base 2 of n. But as we just established a moment ago, that this is just 2 to the power of k, because k is the ceiling of log base 2 of n. So this right here, just to be very clear, this is h of 2 to the power of k, because that's h of m. So just keep that in the back of your mind. So now I have this series, and I would like to do, so remember, I know that this is actually a relationship that h of n has with h of m. So now what we're going to do is as follows. I'm going to come up with a second series that's going to bound this one. And I'm going to do this very cleverly, and this is a common trick with dealing with harmonic series, is I'm just going to make it so that when I add parts of this sum, I'm going to do it like a bucketing approach like I did before. I'm going to use that bucketing idea I had to argue the size of the inequalities, but at the same time, I'm going to lump them into their own finite series. So watch this. Then we can formulate a second series as follows. And I'm going to do this on the right-hand side below. So watch this. So I'm going to take each one of these terms, and I'm going to group them in the following way. So watch this. And keep in mind, there is a way to formulate this in a discrete way. It's very easy to do, but the thing is, it really doesn't add anything to our exercise. So I'm not going to do that here. It's a lot more arithmetic than we need actually here. So I'm going to take each one of the terms I have here in this sum. Why? Because it's bigger than this, right? So if we can get something that involves this, and we can derive a C or something like that from there, then most certainly, if I find it for this larger sum, then most certainly it'll cover this one, the original one, H of N. So I have 1. So the first term right here is I have a 1. You can agree with me that 1 is less than or equal to 1, right? That's not too scary, right? Now I'm going to take the next two terms. So I'm going to take these next two terms. So I have 1/2 plus 1/3. Well, I'm just going to take 1/2, then I'm going to add another 1/2. So I'm going to compare 1/2 against 1/2, and I'm going to take 1/3 and I'm going to compare it against 1/2. Notice that 1/3 is less than, or in fact, it is less than 1/2, right? So I'm going to take each one of these terms, I'm going to take them in increasing powers of 2 many terms together, and I'm always going to write that by the next power of 2 that's on the right-hand side. Notice I have, this would be 1/1. This is going to be 2's in the bottoms. Next one's going to have 4's in the bottoms, but I'm going to have 4 of them. And then I'm going to have 8 of the 1/8's on the right-hand side. Then I would have, and so on. It's like 16 of 1/16's, and so on and so on. So watch this. So the next one would be 1/4 plus 1/5 plus 1/6 plus 1/7. These are all going to be less than or equal to 1/4 because 1/4 is in fact larger than all of these ones, but it's equal to 1/4. So what I'm doing is I'm going to be bucketing everything on the left-hand side, which is this, and I'm going to have this new series on the right-hand side, which is going to end up being at least as big as whatever's on the left-hand side, okay? That's because each one of these is less than or equal to whatever's on the right-hand side, by the same reasoning we've used before. So notice that you can keep writing this out, and you'll end up with 1/2 to the power of k minus 1 plus 1/2 to the k power, 2 to the k minus 1 plus 1. But it's a plus 1, it's not part of the exponent here. I'm just giving you a general form for this. Plus 2 to the power of k minus 1. So notice it always goes up to, but not to the next power of 2 on the left-hand side. And then I just have here 1/2 to the power k minus 1 plus 1/2 to the power k minus 1 plus all the way to 1/2 to the k power minus 1. And this right here is done exactly to the power k minus 1 times. Then there's one last term I haven't accounted for. It's this one right here. So then I have 1/2 to the power of k. Sorry, it's getting a little small here. 1/2 to the power of k. This is less than or equal to 1/2 to the power of k, right? So now I have two buckets that I'm going to have. The left bucket and the right bucket. Notice everything on the left-hand side, when I sum all of those, it has to be at least as big as my everything in the right bucket, okay? So let's put it all together, and let's watch what happens. We're almost there, believe it or not. Because what's going to happen is we're going to put this all together. Then we'll end up with something that will come back to our bookkeeping that we had earlier. And then they'll spit out C at us, and then we'll have N0. If we're clever enough. Keep in mind, like I said, we just need a C and an N0. I was about to say an N0. That's kind of weird. So, H of N is less than or equal to H of 2 to the power of K, which this is less than or equal to 1 plus 1/2 plus 1/2. Now remember, this is that, I'm taking each one of those lines one after the other. So 1/2 plus 1/2, then I have 4 1/4, then I would have 8 1/8. So 1 over 2 to the power k minus 1 plus 1 over 2 to the power k minus 1 plus all the way up to 1 over 2 to the power k minus 1. Then I would have the plus 1 over 2 to the power of k at the end. But here's the cool part. I deliberately picked the things I did on the right-hand side. Do you notice anything interesting going on with these? So notice I have 2 1/2. I have 4 1/4. I will have 8 1/8. I'll have 16 1 over 16s, and so on. I have 2 to the power of k minus 1, 1 over 2 to the power of k minus 1s. These all sum up to 1. So that's a 1. This sums up to 1. This all sums up to 1. So I have 1 plus 1 plus 1 plus 1. But how many of these do I actually have? I have this plus 1 over 2 to the power of k, right? But that just means this is going to be, okay, it's 1, 2, 4, 8, 16, and I have this happening for each one of these. But notice it starts at, so I have 1, 2, 3, 4, but notice it goes up to k minus 1. But notice that it does this for each one of those. So it means it's going to be k plus, so I have k minus 1 many of those, then I end up having this 1 here. And I have plus 1 over 2 to the power k. So notice I'm just adding up all the ones, how many there are, and I add 2 to the power k because that's the last term in this series, this finite series. Now, here we go. Here comes the bookkeeping, okay? Recall, k is equal to the ceiling of log base 2 of n. And n is less than or equal to m, which is equal to the power k, right? So now observe the following. Observe that for all n greater or equal to 1, that h of n is less than or equal to k plus 1 over 2 to the power of k, right? That's because we know this relationship between h of n and h to the power h of 2 to the power k. And then, well, what's k? K is the ceiling of log base 2 of n. Plus, well, 1 over 2 to the power of k, this is just 1 over m. Well, this, the ceiling of this, so if I round up log base 2 of n, it's either going to be a power of 2 or it's going to be 1 higher than that. So keep in mind, if this is a power of 2, it'll end up being literally this, and it's an integer. Otherwise, it's a fractional number. It gets rounded up to the next highest integer. So I could cover this by bounding it, so I can say this is all less than or equal to log base 2 of n plus 1. So I'm just going to add 1. So I stress that this is together. I'm just adding 1 to cover this rounding up process. And now remember, n is less than or equal to m, meaning that I can replace the n here, sorry, the m there with n. But here's the thing. N is greater or equal to 1, right? So that means that 1 over n will never exceed 1. It'll always be 1, 1/2, 1/3, etc., etc. It could be any one of those. So that means this is all going to be less than or equal to log base 2 of n plus 1 plus 1. But what's this? This right here is just equal to log base 2 of n plus 2. That seems awfully simpler to play around with. So now the question is, okay, what do we do with this? So we're going to play the lookalike game, just like what we started off with. Okay, so now I have h of n is less than or equal to log base 2 of n plus 2. So what I need to do is I need to do something that makes this so that it's a little easier to play around with. Because remember, I need to get something like h of n is less than or equal to c times log base 2 of n. So notice that if I were to try to make this 2 look like a log base 2 of n, then maybe picking c is equal to 2 might be a good idea, because it looks like something like this, right? I want something that looks like this. So I need 2 logarithmic terms to cover log base 2 of n and this 2 here. I could have picked c is equal to 3, that also works, but I'm going to pick c is equal to 2. Pick c is equal to 2, then we find n0 so that h of n is less than or equal to 2 times log base 2 of n for all n greater or equal to 1. Well, let's put it all together. We got one last step and then we're done. Now, I'm going to take advantage of the fact that I know that a logarithm is an increasing function. So that's a fact that you can prove using induction or calculus. But I'm just going to take that as a fact, okay? It seems like a pretty reasonable thing for me to presume. Now, if you're not sure what I mean by increasing function, if you look at the shape of, if I plotted this out in a chart, the shape of a logarithmic function will look something like this, but it always goes up. It always goes up. It doesn't plateau. It doesn't go down. If I look at its chart, it only goes up. That's what we mean by an increasing function. So notice that when n is greater or equal to 4, h of n is less than or equal, remember that we established this earlier, log base 2 of n plus 2, right? H of n is less or equal to log base 2 of n plus 2, which this, if we pick n is greater or equal to 4, I should also mention, and log is increasing. That's another reason what I'm doing here. This is less than or equal to log base 2 of n plus log base 2 of n. This is because log base 2 of 4 is equal to 2. So that's why I picked 4. It's because I needed to be big enough that it's equal to 2 or greater. So this is going to be at least log base 2 of 4, which is equal to 2. Which this is equal to, of course, well, log n. This is equal to 2 log base 2 of n. And we're done. So now I just have to choose n0. You'll notice that this is a different choice this time. This is because of the nature of the logarithmic function. It's one common pitfall students fall into, is they forget that the logarithmic function isn't a polynomial. It doesn't operate like that. You have to keep in mind what values it takes. So choose n0 is equal to 4, and then we can say therefore. So now we have c and n0. I'm going to present it to them. I'll say therefore by the definition of big O, h of n is big O of log base 2 of n. And that completes the proof. Very slick, right?